Today we're going to talk about an extremely useful theorem in commutative algebra. This is the so-called prime avoidance theorem. This theorem says the following. So if S is a subring or an ideal of some ring R, and PI's are prime ideals of R, then we cannot have this picture. That is, if S lies inside the union of the PI, then S must lie completely inside at least one of the PI. In other words, if S does not lie completely inside any of these PI, then S cannot be contained in the union of the PIs, i.e., there is some element C of S avoiding all of the PI. That's why this is called prime avoidance. Note that the hypothesis of this could be weakened to assume that at most two of the PIs are not prime. But we'll prove this statement in the case when all of the PIs are prime. Alright, so let's do that by induction. Let's start with two primes and assume that S lies inside the union of P1 and P2. Now, by contradiction, suppose that S does not lie completely inside either of these PI. Now, since S doesn't lie completely in P2, we should be able to find some element A1 of S outside of P2. Observe that since S lies inside the union of P1 and P2, A1 must lie inside P1. Similarly, since S does not lie completely inside P1, there must be some A2 in S that is outside of P1. And thus, A2 must lie inside P2. Now let C be the sum of A1 with A2, then clearly C lies in S because S is closed under addition. But we claim that this C does not lie inside this union. This C does not lie inside either P1 or P2. To see that C does not lie in P1, observe that A1 lies in P1, but A2 does not lie in P1, so their sum cannot lie inside P1. And the similar argument shows that C does not lie inside P2. Thus, we found an element of S that is not contained inside the union of P1 and P2, and that's a contradiction. Alright, so we have proved the theorem for the case when n is equal to 2. Now we want to do the inductive step. To illustrate the inductive step, it suffices to just look at how we go from case n equal to 2 to n equal to 3. So let's do that. So let us assume that S is contained in the union of P1, P2, and P3. Now, if S is contained in the union of any two of these PIs, then by the previous case, we already know that S must lie strictly inside one of the PI. So let us therefore assume that S does not lie inside the union of any two of these PIs. Since S is not contained inside the union of P1 and P2, there must exist some A3 in S that does not lie inside P1 or P2. But S is contained in the union of these P1, P2, P3, so A3 must lie inside P3. Using the same argument, we can construct A1, A2 in S such that A1 lies inside P1, but A1 does not lie inside P2 and P3, and A2 lie inside P2, but A2 does not lie inside P1 and P3. Then we claim that the following element C is in S, but it does not lie inside any of the PI. So why is that? Well, A1, A2 lies inside P1 and also P2, but A3 doesn't lie inside either of these, so the sum cannot lie inside P1 and also cannot lie inside P2. Similarly, as A1 doesn't lie inside P3 and A2 does not lie inside P3, then since P3 is a prime ideal, we know that this product A1, A2 is not inside P3. So then, this sum cannot lie inside P3. And thus C does not lie inside any of the PIs. This contradicts the assumption that S lies inside the union of the PI. Therefore, our hypothesis must be wrong. And thus S must be contained in the union of two of the PIs, which by the previous case means that S is strictly contained inside one of the PI. And that's the proof of the prime avoidance theorem.